This research paper introduces three approaches for classifying protoneutron star (PNS) oscillation modes, which is crucial for understanding the physics inside PNSs and detecting gravitational waves (GWs) from galactic core collapse supernovae. The authors apply the Cowling classification, Generalized Cowling Nomenclature (GCN), and classification based on Modal Properties (CBMP) to PNS models from 3D simulations of core collapse supernovae. In the early stages of PNS evolution, the Cowling classification is inconsistent, while the GCN and CBMP provide complementary information that helps understand the evolution of the modes. The GCN reveals avoided crossings as the mode frequencies evolve at early times, whereas the CBMP tracks the modes across these avoided crossings. The strongest emission of GWs by the PNS corresponds to the F mode in the GCN, indicating that the mode trapping region alternates between the core and the envelope at each avoided crossing. At later times, the three classification methods present a similar description of the mode spectrum. The authors use their results to test universal relations for PNS modes according to their classification and find that the behavior of the universal relations for F and P modes is remarkably simple in the CBMP. The paper also discusses the complexity of the processes during core collapse, which renders it impossible to predict with high precision the resulting GW waveforms. However, the community has reached some agreement on the key aspects of the signal morphology after several years of numerical simulations. The authors use a theoretical framework developed to study stellar perturbations to describe the GW signal of a supernova as the superposition of the oscillation modes of the PNS. Oscillation modes of stellar configurations can be classified by taking into account their main restoring force, with pressure being the dominant force for P modes and buoyancy for G modes. The paper presents the setup for calculating the non-radial oscillation modes from PNS described by data from core collapse supernova simulations. The authors use a Lagrangian description of the fluid perturbation, following Morozova et al. 2018, and apply linear perturbation theory to the PNS. The results obtained using the three different classification methods are presented, along with a brief analysis of the universal relations of PNSs. In this study, the authors present a comprehensive analysis of the non-radial oscillation modes in a post-supernova neutron star (PNS), using three different classification schemes: the Cowling classification, the Generalized Cowling Nomenclature (GCN), and the classification based on modal property. The PNS models used in this work are derived from 3D simulations of core collapse supernovae by Radice et al. 2019. The oscillation frequencies and their respective eigenfunctions are computed using a shooting method with Ritter's root-finding algorithm to solve a set of four first-order coupled differential equations for the fluid perturbations, in the relativistic Cowling approximation. These equations are solved at every time step of the PNS evolution. The authors first use the Cowling classification, which is based on the number of nodes in the radial eigenfunction. In this scheme, the fundamental mode has 0 nodes, and each P mode and G mode has n nodes, with n being a positive integer. However, this classification does not account for the evolution of the star, and the relation between the number of nodes and the mode number is not direct. The GCN classification, on the other hand, takes into account the evolution of the star and considers the difference between the number of P nodes and nodes, denoted as n. This classification scheme conserves the mode number as the star evolves and can distinguish between P modes and G modes based on the sign of n. The authors also introduce a third classification scheme based on modal property, which complements the GCN classification by representing the character of the mode. This scheme is introduced by Shibahashi and Osaki, 1979, and is more appropriate for evolved stars. The propagation diagram in Figure 1 illustrates the normalized Brunt-Väisälä and Lamb frequencies for a PNS model, with the P propagation zone and G propagation zone marked accordingly. The phase diagram in the central panel of Figure 2 shows the eigenfunctions for the modes depicted in the top panel, with the nodes classified as P nodes or nodes based on their direction in the diagram. The bottom panel of Figure 2 illustrates the frequency spectrum of the PNS, with the number of nodes in the radial eigenfunction marked for each mode. The study demonstrates that the GCN classification is more suitable for evolved stars, as it conserves the mode number throughout the star's evolution. The classification based on modal property provides complementary information about the mode characteristics and their evolution. The authors conclude that the use of these three classification schemes provides a comprehensive understanding of the non-radial oscillation modes in a PNS, which is crucial for interpreting the asteroseismic data from gravitational wave observations. Here is a combined summary of pages 5 and 6 of the research paper. The authors present three approaches for classifying PNS, protoneutron star, modes. The Cowling classification, the GCN, Generalized Cowling Number, and the CBMP, core envelope-based mode phenomenology. The Cowling classification involves counting the number of nodes of the amplitude of the radial Lagrangian displacement and comparing the frequency with that of the F mode. The GCN method classifies modes based on fixed values of n, which increases monotonically with frequency. The CBMP approach classifies modes according to whether they are trapped in the core or envelope of the PNS, using the ratio of kinetic energy of the oscillation mode within the core to that of the whole star, delta. The authors apply these classification methods to 10 models of PNS evolution, focusing on the quadrupolar, L equals 2, modes in the frequency range 1,002,000 Hz. The results show that the Cowling classification is not well defined at early times, while the GCN and CBMP methods provide a simpler and more consistent description of mode evolution. The GCN method reveals avoided crossings between modes, whereas the CBMP approach identifies modes trapped in the core or envelope, with the delta threshold distinguishing between the two. The authors also investigate the time evolution of mode frequencies and classify modes using the three approaches. They find that the GCN and CBMP methods provide complementary descriptions of mode evolution, with the GCN revealing avoided crossings and the CBMP identifying changes in mode character. The authors illustrate the evolution of the F mode, which gains and loses pairs of p and nodes, changing its Cowling classification but keeping n constant in the GCN. Finally, the authors discuss the emission of gravitational waves by the PNS, comparing the time-evolving spectrum of modes with the spectrogram of the GWs for one of the models. They show that the GCN and CBMP approaches can help identify the modes contributing most to the GW emission. In the context of post-supernova neutron stars, PNS, asteroseismology is a complex field due to the dynamic and temperature-dependent nature of these celestial bodies. This paper explores three different methods for classifying non-radial modes of oscillation in PNSs: the Cowling classification, the Generalized Cowling Approximation, GCN, and the Brunt-Väisälä frequency matching procedure, CBMP. The standard Cowling classification is not well defined for PNSs, as it relies on identifying a fundamental F mode without nodes, which is not present at early times after the bounce. The GCN method, on the other hand, allows for the identification of P and nodes, enabling the tracking of mode evolution. It reveals marked avoided crossings at early times, where two modes exchange character. The F mode identified with the GCN shows good agreement with simulated gravitational wave, GW, emission, indicating that the region responsible for most of the GWs rapidly alternates between the core and envelope of the star at early times. The CBMP follows the time evolution of sequences of modes with the same properties, such as being trapped in the core or envelope. This approach produces a remarkably simple and monotonic behavior, as avoided crossings are absent. The paper presents fits for quasi-universal relations describing the most relevant mode frequencies as functions of the PNS average density, independent of the progenitor mass. These relations are similar to those proposed for cold neutron stars, but with a minor influence of the equation of state, EOS, for dense matter. The matching classification scheme of Torres-Forney et al. 2019b produces results qualitatively similar to the CBMP, showing no avoided crossings at early times and a mode compatible with the G0 mode, classified there as a G2 mode. The ramp-up mode discussed by Mori et al. 2023 is similar to the F mode described by the CBMP. One of the main advantages of the CBMP is that it provides physical information relative to the part of the PNS where GWs are most likely being produced. Future directions for this work include extending the GCN and CBMP methods to better understand the PNS spectrum and its evolution with avoided crossings. This research aims to provide insights into the asteroseismology of PNSs, which could be crucial for understanding the physics of these objects and their role in GW emission. The paper discusses the classification of postmerger neutron star (PNS) modes using two approaches: the Cowling approximation-based mode pattern (CBMP) and the gravitational wave (GW) network (GCN). The CBMP method is based on the Cowling approximation, which neglects the perturbation of the gravitational potential, while the GCN considers the full linearized Einstein equations. Both methods are applied to a set of simulated PNS models, with varying mass and radius. The study reveals that the GCN better captures the complex behavior of the PNS modes, especially in the low-frequency regime. The CBMP, however, provides simpler trends in the mode frequencies due to the absence of avoided crossings. The authors also explore the relationship between macroscopic quantities such as mass and radius, and the frequencies of the classified modes. They find that the GCN sequences exhibit more variability than the CBMP sequences, which is attributed to the presence of avoided crossings in the GCN. The paper highlights the importance of considering the full linearized Einstein equations for accurate mode classification, particularly for the study of PNSs. The paper also discusses the use of machine learning techniques for classifying PNS modes, which can significantly reduce computational costs compared to traditional methods. It is suggested that these techniques could be applied to simulations with different progenitor masses and additional equations of state, AOS, to further validate their performance. In conclusion, the study presents a comprehensive comparison of two methods for classifying PNS modes, emphasizing the importance of considering the full linearized Einstein equations for accurate mode classification. It also explores the potential of machine learning techniques in simplifying the process of mode classification, paving the way for future research in this area. The authors present three approaches for classifying PNS modes, focusing on the CBMP method, which categorizes modes based on the region in the star where they are trapped. This classification depends on the ratio of the kinetic energy of oscillations within the core to that of the whole star, denoted as delta. The authors investigate the impact of varying the critical threshold value, delta critic, on the classification of modes. Figure A1 displays the time evolution of mode frequencies after the bounce, using the CBMP with different values of delta critic between 0.2 and 0.5. The results show that the core-trapped G0 mode becomes slightly more prominent with decreasing delta critic. The modes change character at different times for each case, with larger delta critic values resulting in modes trapped in the core envelope, becoming trapped in the envelope core earlier, later, compared to smaller delta critic values. The authors find that for 0.2 is less than or equal to delta critic is less than or equal to 0.5, the results are qualitatively the same, indicating that the CBMP method is robust to variations in the critical threshold value. This suggests that the classification of modes is not highly sensitive to the specific choice of delta critic within this range. The time evolution of mode frequencies is characterized by the gradual change in mode character as the star evolves. The G0 mode, in particular, exhibits a significant change in its frequency and amplitude over time, indicating a transition from a core-trapped to an envelope-trapped mode. The author's investigation highlights the importance of carefully selecting the critical threshold value in the CBMP method to ensure accurate classification of PNS modes. The results demonstrate the robustness of the CBMP method to variations in delta critic, providing confidence in its ability to accurately categorize modes in PNS. The analysis presented in this appendix provides a detailed understanding of the CBMP method and its dependence on the critical threshold value. The findings have implications for the interpretation of PNS mode classification and the development of more accurate models of stellar oscillations.